All right, welcome back, physical science class. It is time for another video. Today we're covering three topics. They're very short. They're kind of skill-based, so we're just going to go straight through them. Periodic trends, drawing Bohr models for atoms, and drawing Lewis dot structures for atoms. Okay. Now again, like I always say, make sure that if any of this is not making sense to you, pop into my office hours, pop me a question in my email, on Teams, whatever you need. Meet with me privately, set up a time for us to meet on Teams. Any of those are viable options, especially if you're struggling. Hey, guys, I have to admit this stuff is not easy. Okay? Especially online where I'm not there to clarify quick questions for you. If you are getting stuck, please reach out. Please set up a time for us to meet. All of those things, and I guarantee you that I can help you through this. If you just want to meet and go over your assignments, I can do that. I can take you through assignments. That's what I'm here for. Literally, I sit at home waiting for people to contact me, and for physical science, it seems like that never happens. I don't know why, but if you look at earth science versus physical science, almost every single one of my earth science kids reaches out, turns in their work, and then only about 50% of physical science kids do. Okay, so let's get into it. Okay, make sure that if there's a part that you need clarification on, that you are reaching out so that you can pass this class. All right, so let's start with periodic trends. There's 5 that we are going to talk about in this class. Atomic radius, electron affinity, ionization energy, electronegativity, and metallic characteristics. Okay, now, obviously these are very, very sciencey words, okay, but we're going to try to break them down into the simplest terms possible. Okay, so let's talk about atomic radius. The typical excuse me, still getting over my sickness. The typical distance from the nucleus of an atom to its outermost electron shell. Okay, so all this is talking about is if you drew an atom, let's say, actually I'm just going to use this circle right here. Okay, let's say there's a nucleus in here. It is literally just how far it is from the nucleus out to the outer part of your atom. Okay, so it's just a distance. Okay, so the bigger the atomic radius, the bigger the atom, or the wider the atom. Okay, electron affinity is next. This is also called the effective nuclear charge. Okay, this is the strength of the positive attraction from the nucleus. Okay, so as this goes up, the positive attraction from the nucleus goes up. Okay, so essentially what that means is the more positives you have in the nucleus itself, obviously the stronger the attraction is going to be. And I'll show you on the periodic table how we find these trends and what they're related to, and that whole thing on a next slide. Okay, next up next up we have ionization energy. This is the energy required to remove the most loosely bound valence electron. So if you imagine, if I go back to my circle here that's going to represent my atom, let's say that I have an electron sitting out here on the outermost shell. The ionization energy is the amount of energy it takes to remove that. Okay, so if you imagine for bigger elements, okay, as the electrons get farther from the nucleus, it is much, much easier to take them. Okay, if I have a very, very small atom, let's say that I have one like this, and the protons are this, and let's say the electron is right here. Notice that the distance here isn't very great. That means that this positive nucleus is pulling on that electron, and it's going to be difficult to remove that electron. Whereas as we get bigger elements, hey, it's a lot easier to take this. Okay, something else that comes into play is that it also depends how many are in the outer shell in order to take. Okay, so and we'll talk about these rules here in a second, but there's rules for electrons when they leave an atom, whether an atom wants to gain electrons or lose electrons, and it has to do with the ionization energy as well. All right, next up we have the electronegativity. This is the tendency of an atom to attract electrons to itself when bonded to another atom. Okay, so again, this is going to talk about its likelihood to gain electrons versus lose them. You'll notice that these two things, actually really these three things, okay, they are all very related, these three. And we're going to have to try to keep them straight as we go forward, but they all have to do with the electrons, okay, and how much we lose or gain them. Okay, so some atoms, for example, oxygen is more likely to gain electrons rather than give away electrons, and we'll see why here in a little bit, and when we do some practice, hopefully it'll make more sense then too. The last thing that we're going to talk about is metallic characteristics. Okay, so obviously on your periodic table there are some metals, there's some metalloids, there's some nonmetals, and these are just describing the physical properties associated with metallic atoms. So metals are shiny in appearance, they have a high density, they have high thermal conductivity, and high electrical conductivity. So all this is going to be is if I ever asked you between two elements, hey, is this element more conductive than this element? Explain why. And you would refer to, well, zinc is more of a metal than oxygen, so then it'd be a better conductor of electricity. Okay, that's all you would have to do on a quiz or a test or anything like that. Okay, so here is the visual that goes along with the periodic trends. You'll notice that there are a couple things I want to point out. Okay, the arrows point in which the way that things increase. So you'll notice that the atomic radius, we'll start with atomic radius, increases as you go to the left in your periodic table. Okay, and it also increases as you go down, making this bottom left corner the biggest or the highest radius. Okay, and I think if I remember off the top of my head, I think it's like francium or something like that. But either way, it has the highest radius, meaning that it is the most spread apart. Okay. Now, you'll notice a lot of these actually still match themselves. So let's look at electronegativity, okay, and ionization energy. They both increase going to the right. Okay, and then lastly, we have electronegativity increases as we go up, and ionization energy increases as we go up as well. Okay, so that means, now, the one thing I am going to mention, okay, the exception to these rules in this last column, what we call the noble gases. We call them the noble gases because they don't really like to react with anything. So we kind of forget about them as far as like losing electrons or gaining electrons because they are in a stable position. Okay, they have everything that they want and they don't want to associate themselves with anything else. Okay, so really what these trends are for, and I would definitely write these down so that you can refer to them when I ask, you know, if oxygen here has a higher electronegativity than this one over here, you would say yes, because obviously it increases as you go right. So things to the right are going to have a higher electronegativity than things to the left. Or if I say, does this box have a higher electronegativity than this one? You would say yes, because it's above that one. Okay, again, if these trends don't make sense on how you're going to use them, what it boils down to on the test is comparing them between each element. So I may ask you which which element is it more difficult to take an electron from? So that would be ionization energy. And so this element up here is actually one of the most difficult to take an electron from, and down here is one of the easiest to take an electron from. Okay, and so those differences are the ones that you guys need to know. Okay, so we'll do some practice with that in some of your assignments. The other thing that we didn't talk about yet, metallic characteristics in here. Okay, so things get more metallic as you go down into the left and more non-metallic as you go up into the right. So these up here, let me get a better color. These up here are non-metals, okay, non-metals on our periodic table. And everything over here is going to be metals. Okay, and then we have metalloids actually in there. But either way, as you go down into the left, you get more metallic. As you go down into the left, you get a higher radius. As you go up into the right, you increase in not only electron affinity, but electronegativity and ionization energy. Okay. All right, so like I was saying, there are rules for how we place electrons in atoms of certain elements. Okay, so the first rule is called the duet rule. This says that the first inner electron shell can only hold 2 electrons. So for example, if you have your nucleus here and you have your first electron shell, this one can only hold 2 electrons. Okay, that's all it's saying. No matter what, it only has 2 electrons. The octet rule, excuse me, the octet rule says that every shell after that can have upwards of 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay? To be stable like a noble gas. Elements larger than phosphorus are an exception to this octet rule. Yeah, they have different electron levels that we're not going to really get into in full depth. That would be more for if you want to take a chemistry class specifically. They'll get more into that. For physical science purposes, we're just going to leave it at the duet and octet rule and leave that for chemistry. These two rules also determine how an element will react when bonding with other elements. That is actually our next unit when we talk about different types of bonding, which is ionic and covalent, and we talk about that and how that all works. But that is actually next unit, which leads me to our unit test is coming up very shortly, probably next week, over everything about the atom, from the history of the atom to its parts, okay, nucleus, all that stuff, isotopes, ions, and then obviously periodic table, periodic trends, and then we'll have Bohr models and Lewis dot structures on there. Okay, so all of that is going to be on the unit test, so make sure that you're prepared before you get there, and let me know how I can help you along the way. All right, so next part, we are getting into drawing of the Bohr models. These are Bohr models. Okay, if you remember, it was the third model after I think we had billiard ball. Let's see if I can write on here. Billiard ball. Then we had plum pudding. Okay, and we used the Bohr model for drawing because it shows the valence electrons in the best way. They have learned through experimentation that they don't follow these orbitals exactly as they're shown here. But for our purposes, we like to draw Bohr models so that we can get an idea of the valence electrons and how these atoms and elements are made. So all you need to know, let's take an oxygen element for example. Okay, you do not need to draw in the protons and neutrons. You're just going to put one single nucleus in the middle. Okay, and so if you use our duet rule, okay, that means on the next line, there can only be 2 electrons. Okay, so you'll see my 2 electrons there. Okay, if you look at your periodic table, the atomic number of oxygen is 8, meaning it has 8 protons and 8 electrons when it's stable. Okay, so we have 8 electrons on this one, so that means there's going to be 2 on the inner ring. Okay, and then 1, 2, 3, 4, 5, 6 on the outer ring. Remember that the octet rule says you can have up to 8. Okay, so you can have less than 8, okay, but you can't have more than 8. Once you get to 8, you have to start a new ring. All right, so an example of that would be silicon over here. It is the 14th element. Okay, and as you can see, I do the same exact thing. I draw a nucleus with the atomic symbol in the middle, and then we have the duet rule, so it has to have 2 in that one, and then 8 in the next. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 2 here, 8 here. Notice that only gets me to 10. Well, I need a total of 14, so I add 4 more around the outside. So 1, 2, 3, and 4 for that outer ring. Okay, and so when we ask about valence electrons, fancy word to mean outer electrons, okay, silicon would have 4 valence electrons. Okay, and oxygen would have 6 valence electrons. Okay, that's the amount in the outermost ring. Okay. All right, so let's practice a little bit. So we have hydrogen here. Okay, we know that hydrogen has an atomic number. Let's see if I can write better. Of 1, meaning it has 1 proton and 1 proton and 1 electron. So we start by drawing the nucleus and putting H in the middle because that's the symbol for hydrogen. And then I am going to do this in a different color. It has 1 electron shell. And since it has an atomic number of 1, it only has 1 electron. And that is all you would do. Okay, hydrogen has 1 nucleus, and then it has 1 shell. Okay, notice again, that's the duet rule, can only have 2. Well, I only have 1, so I can't go any more than that because that's all I have. Okay, and that's all you have to do for Bohr models. Okay, so if we start with the next one, nitrogen, start with our nucleus, start with our symbol, which is just N. I'm going to double check. I believe nitrogen is the 7th element, but I'm just going to make sure before I tell you something completely wrong. And I'm going to look again on ptable.com. That's the easiest one to go to. Nitrogen is in fact the 7th element, so the atomic number is 7, meaning I have 7 electrons. So I'm actually going to move my nitrogen over here more. Nitrogen, there we go. Okay, I'm going to draw my first electron orbit. And if you remember, I can only have 2. So I put 1 electron there, 1 electron there, and then I have to draw a new orbit. So we go another one. Okay, now this one can have up to 8. Okay, but I only have, so that's 1, 2 already. Okay, if I subtract that from the 7 I know I have, that means 5 are going to go in this outer one. So I start with 1, 2, 3, 4, and 5. And that's my Bohr model, and I am done. Okay, the next one, iron. Okay, if you're looking for iron, make sure you're looking for Fe on your periodic table. And this is the atomic number is 26, I believe. Let me find it. 26. Okay, so this one's going to be a little bit bigger, so I'm going to go out here. So we have Fe. There's its nucleus. Its first layer, again, is only going to have 2 electrons. Okay, so if I take those 2 away from my electrons, I've got 24 more to place. Okay, so what I'm going to do is I'm going to place 8 in this one. 2, 3, 4, 5, 6, 7, 8. I kind of did not evenly space those out. Let me see if I can. Oh, I erased my circle. See if I can draw this in here again. I'm going to do that, and I'm going to put the 8th one right there. Okay? Now, here is again where, let me double check something. Okay, so this is where things get tricky with iron, and this is where this goes beyond our class. So I'm just going to explain it real quick, but it has to do with and I kind of just wanted to do it as an example of what you guys will be doing if you take a future chemistry class. So the next layer will all depend on different electron energies. Okay, so what ends up happening is that you can end up having up to 18 in some of your layers. So if you notice, 26 went down to 24 after that one. If I go down again, I subtract 8 and I get 16. Okay, what ends up happening is I actually get 14 in the next one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, and again, like I said, this is outside the realm of this class. I'm not going to have you guys do this complicated of Bohr models, especially because we're going to do Lewis dot structures, which kind of simplify this process a little bit even more. Okay, and then if you imagine that was 14, so I take away 14 more, I'm left with only 2 electrons, and I place them in the outermost ring, and that is technically what iron Bohr model would look like. Okay, now if that last one confused you, please don't freak out about that. I'm not going to ask you to do ones that complex. I just thought I'd mention past phosphorus, they do get a little bit complicated, which is why we simplify it to the Lewis dot structure, which we're going to talk about next. All right, so we're going to make things easier with just valence electrons. Valence electrons are the electrons in the outermost shell. They're the only ones that react and do any kind of bonding. So like I said here, oxygen has 6. Okay, 1, 2, 3, 4, 5, 6. Okay, so even though it has 8 total, it has 6 valence electrons, and that determines how it bonds to things, why it bonds to two hydrogens to make water so well, and that sort of thing. So let's look at what Lewis dot structures do for us in the simplification of this. All right, so Lewis dot structures, we've got chlorine here. On the Lewis dot structure, only the valence electrons, the outermost shell, are drawn, so you could see only the 7 valence electrons. Okay, so the total electrons minus the first shell minus second shell equals the Lewis structure number. So for example, chlorine has 17. Okay, so 17 minus the duet rule, which is the innermost. Okay, that gives you 15. Okay, then you're going to have another ring in there that can have 8, because the second one can have 8. And that leaves you with 7. That means that I have 7 valence electrons. And so all you do is whatever your atomic symbol is. So for chlorine, it is Cl. That was the worst C of all time. C. And I'm just going to place 7 dots around it. Now, normally we put them in pairs. So we go 1, 2, 3, 4, 5, 6, and 7. Okay, and that's all a Lewis dot structure is. But it's so helpful because it's compact and it tells us the most important information about our atom. Okay, so if you imagine, the hard thing is once you get into elements that are really, really big, you don't want to draw Bohr models that have, 4 and 5 and 6 orbits. All I care about are the valence electrons in the first place, which is why we use Lewis dot structures to simplify that process. So let's get into some practice. Okay, so we already did these same ones with our Bohr model. So let's look at what they would look like Lewis dot structure wise. Okay, so we know the atomic number equals 1. Okay. So again, all I'm going to do is I'm going to draw H for hydrogen because that's its thing. That's its atomic symbol. And I'm just going to put one single dot to represent one valence electron. And that's it. That is all you have to do, and you're all done. All right, moving on to nitrogen. The atomic number was 7. Okay, so again, if you remember, the inner electron shell has 2, so I'm going to take 2 away from that one, and I'm going to end up getting 5. Okay, so notice that I can't take 8 away from that because then I get a negative number. Okay, so 5 must be my number of valence electrons. So I draw N, and I'm going to place 5 around the outside like this. Okay, 1, 2, 3, 4, 5 valence electrons, and then I'm done. Now, remember again that iron was a little bit weird. Okay, the atomic number was 26, but I only had 2 valence electrons because really what ended up happening is I had to do 26 minus 2 to get 24, then minus 8, and then I had to subtract, let me subtract that first, that's 16, and then minus 14 because I was in the next level, giving me 2 valence electrons. So the Lewis dot structure for this one is actually iron, and we go 1, 2. Okay, so there's only 2 in the outer shell for iron. Okay, now that is all that I have for you. I hope that this practice comes to you and is effective. If you get stuck on any, let me know. Come into office hours and I will literally just take you straight through the practice if you need to. Other than that, thanks for watching. Make sure that you do your video check, and we'll be looking forward to doing our unit test next week. Thanks for watching.